Right, in this lesson, we'll look at the nature of radioactivity. And here is a overview of the chapter. We won't cover all of these topics. Nuclear chemistry is the study of reactions that involve changes in the nuclei of atoms, and often this involves changing from one element to another. Radioactivity was originally discovered back in 1896 in Paris. Henri Becquerel was doing some work with phosphorescence and an ore of uranium called pitchblende, and he exposed the ores to the sun, and then he looked at the light that was emitted. Well, it turned out that Paris had several weeks of cloudy, rainy weather, and so he suspended his experiments for a while and put this sample in a desk drawer wrapped in paper, and he happened to put it next to a radioactive or a photographic plate. And several weeks later, he decided to go ahead and develop the plate, and discovered that the pitchblende had actually exposed the plate, even though it hadn't been exposed to the sun. Marie and Pierre Curie helped him to explain this phenomenon, and Curie's coined the term radioactivity. It was actually something that didn't have anything to do with phosphorescence. The Curies also discovered polonium and radium, which are both radioactive elements. Rutherford used alpha particles from uranium to bombard gold foil, and from this he developed the nuclear model of the atom. Radium in the early 20th century was used in such places as luminescent paints. There were ointments. There were spas where people were exposed to radium. And of course, this resulted in many instances of cancer and other diseases. Okay, nuclear reactions involve unstable nuclei, and at the end of a decay chain, the process stops when a stable isotope is formed. These are some of the uses of radioactivity. Okay, can be used to generate electricity, diagnose disease, and treat disease. Okay, and talking about stable versus unstable elements, let's move on to this chart. Here we have a graph of the number of neutrons versus the number of protons. And this shaded area is what's called the belt of stability. Okay, so these are the stable isotopes. And for light elements, this happens when the ratio is about 1 to 1. But then for heavy elements, the ratio is about 1.5 to 1. Okay, the heaviest stable isotope has atomic number 82. It's lead, and it's lead 209. Okay, anything beyond that is not stable. Okay, so these dark colored spots here, these represent stable isotopes. Okay, here is a summary of the various subatomic particles, their symbols and their masses. Neutron has a mass which is very similar to that of the protons, just very slightly heavier. Electrons are much smaller than protons or neutrons. Deuterons are particles in which a neutron and a proton are fused together. The alpha particle is actually a helium nucleus. It has two protons and two neutrons. And then there's the positron, which has the same mass as an electron, but it has a positive charge instead of a negative charge. Okay, first we'll look at beta decay, and this occurs when we have too many neutrons, okay, in which we have a neutron-rich nucleus. An example is carbon-14, and carbon-14 undergoes beta decay to produce stable nitrogen-14. Okay, to balance this equation, we add up the subscripts and the superscripts. 0 plus 14 is 14, minus 1 and 7 is 6. Okay, so this is how we balance nuclear equations. Okay, alpha decay occurs mainly where the atoms are just too big. So this is the major decay mode among the heavier elements, such as uranium. Uranium-238 undergoes alpha decay to produce thorium-234. Okay, so the bottom number is the number of protons. The top number is the mass number, which is protons plus neutrons. Okay, so if we take the difference between 238 and 92, that would tell us how many neutrons were present. Okay, so again, we add up the superscripts. 234 plus 4 is 238. 90 plus 2 is 92. Okay, so here's one of 4 naturally occurring radioactive decay chains. And on this particular one, which starts with uranium-238, the end of the chain is stable lead-206. Okay, so uranium-238 undergoes alpha decay. So there is a decrease in mass of 4, and the atomic number decreases by 2. And then it undergoes 2 beta decays. There's no change in the mass number, but there's an increase in the atomic number by 1. So it's alpha, beta, beta, and then alpha, 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 okay, and so on, until we get to lead-206. Right, a positron is a particle with the mass of an electron, but with a positive charge. And this is the principal mode of emission from nuclei that don't have enough neutrons or neutron poor. Carbon-11 is an example. This is an artificially produced isotope. And when it decays by positron emission, the byproduct is boron-11. So again, we add up the subscripts, we add up the superscripts. Electrons and positrons are examples of antimatter. The positron is an antiparticle of the electron. And when these collide, they annihilate each other. 2 gamma rays are produced. Okay, so we add up the subscripts. Plus 1 and minus 1 is 0. 0 and 0 is 0. So gamma rays have no mass and no charge. Okay, they are pure electromagnetic radiation. So gamma rays are high energy electromagnetic radiation, very penetrating. It takes lead or concrete to stop them. They have essentially no mass. They are generated in stars and also on Earth from terrestrial sources. They can permeate outer space. Okay, we can detect gamma rays in our observatories. They are absorbed by gases in our atmosphere. And because they're very high energy, they can disrupt both cancer and normal cells. Okay, another mode of decay is what's called electron capture. And again, this is one that takes place in neutron poor isotopes such as carbon-11. Earlier, we saw carbon-11 undergoing positron emission. Okay, it could also undergo electron capture, okay, in which an electron close to the nucleus is captured, and the electron combines with a proton to produce a neutron. Okay, so I'm going to go ahead and stop here.